telephone system can turn your voice into short flashes of laser light travelling along a strand of the world's purest glass. This glass thread, finer than a human hair, is called an optical fibre. British Telecom, together with others in the telecommunication industry, is using the application of science to rewire Britain. Glass cables are going under the ground, on overhead poles, and underwater. Soon, an optical link will join Britain with Europe. Light is just one part of the electromagnetic spectrum, which also includes radio waves. We're used to the idea of radio waves carrying speech and music, but light can do this too. This light-emitting diode, called an LED, is controlled by a sound amplifier. Together they make up a light transmitter. The light receiver is this photodiode with its own amplifier. Music from the cassette causes the LED to vary its brightness, variations that are picked up by the receiver and turned back into music. A prism can redirect the light. Optical fibre is the best way to conduct light signals. While LEDs, photodiodes and optical fibre are new, using light to send messages is not. The ancient Greeks flashed messages using their shields to reflect the sun. The arrival of the Spanish Armada was signalled by coastal bonfires. And during World War II, Aldis lamps were used at sea for Morse code. Light signals sent through the air have limited uses. You must have line of sight, which means short range. And of course, the light path can easily be interrupted. In the past, light has not been used for telecommunications, as there was no way to channel it across long distances. It can't be broadcast like radio waves, nor travel along metal wires like electricity. The invention of lasers in 1960 prompted scientists to start work on a cable to carry light. From the start, they knew they could send light down a short length of glass, because the physics of light reflection and light refraction would make the signal bounce along the glass. This experiment uses a ray box and a prism. Light travelling through glass into air at right angles is not bent at all. When the light source moves off the 90-degree angle, called the normal, we can see the ray, as it leaves the glass, being bent or refracted away from the normal. The angle of incidence of the ray increases, and eventually the refracted ray grazes along the surface of the glass. When this happens, the angle between the light ray and the normal is called the critical angle. Increasing the angle past the critical angle, the light stops being refracted and all the light is internally reflected. This is called total internal reflection, and only happens when light is travelling at an angle greater than the critical angle. Light that enters a glass rod always hits the edge of the rod at a greater angle than the critical angle. The light ray is internally reflected to the other side of the rod, where it's reflected back again. If you pick up a block of glass and look through it, you'll see that the inside walls form a perfect mirror. This is due to total internal reflection. Play with the length of optical fibre. It's easy to forget that light inside is still moving in straight lines. The reason is the light keeps on being internally reflected until it finally shines out at the other end. But while the theory works, To make a practical long-distance system is much harder. For one thing, the glass made in the 60s wasn't clear enough. If you look at an ordinary window pane, you'll see that edge on, the glass looks dark green. This is because of copper and iron impurities. A new manufacturing technique was developed to make a very pure glass, which is deposited from a mixture of gases. A glass so transparent that a wall of it, 20 kilometers thick, would be almost invisible. If the oceans were made of this glass, you'd be able to see right to the bottom of the deepest part. But even fibers made from this very pure glass are still not perfect. This glass rod behaves just like a giant optical fiber. Feed light into one end and it reappears at the other. Dimming the room light, you can see that the rod itself is glowing. Light is escaping across the whole surface of the glass. When we touch the glass, we destroy the refraction between glass and air. The critical angle no longer exists, and more light is lost. To prevent light losses such as these, optical fiber is manufactured with a second layer of glass of a type that is less dense than the central core. Because the refractive index of the outer glass is lower, the light is always reflected internally. Finally, to protect the glass, it's coated by a layer of soft plastic and an outer shell of tougher plastic. The individual fibers are then stranded together to form a multi-core cable. Even using all these modern manufacturing techniques, some of the light is still lost from the fiber. One reason is that light inside the glass scatters. The rays change paths, hitting the glass surface at angles lower than the critical angle. They pass straight through. This effect is called Rayleigh scatter. We can demonstrate this effect with white light. This drum contains a kilometre of optical fibre. Switch on the transmitter light, and the coil glows blue from the scatter light. It's the same effect that makes the sky blue. The light that travels all the way through the glass and appears at the other end is red. Red light has a longer wavelength than the blue, so the longer the wavelength, the lower the light loss. This is why the lasers chosen for optical communication give out infrared light, totally invisible to human eyes. We can only see it by using special film. This laser light is coming from the edge of a miniature semiconductor chip. As optical fibers are so thin, the light source has to be tiny too. Laser chips are easy to control, ideal for high-speed digital communications. Electric light gives off a broad spectrum of colors, creating the impression of white light. But lasers only produce light of a single color or wavelength. Because the light is a single wavelength, we call laser light coherent. Light can travel along a fiber in a continuous beam or as digital on-off pulses. Digital signals are made by measuring the analog signal thousands of times a second and producing a series of numbers, each of which is sent down the cable as a binary signal made from on and off pulses of light. No matter how many times the signal is amplified, the same pattern of pulses remain intact. At the distant end, the numbers are transferred back into a faithful copy of the original sound wave. Optical cable carries not only digital voice conversations, but text, data, diagrams, teletext, and television signals. And because they are all digital signals, they can be compressed into minute time segments, allowing many other digital signals to be squeezed into spare time slots. Thousands of telephone conversations or other data travel on the same optical fibre. The amount of information that can be sent along one optical fibre depends on how quickly the laser can switch on and off. Faster flashes means more information. These days, the standard rate is 140 million flashes a second, or 140 megabits. This amount of information will allow almost 2,000 telephone conversations on a single optical fibre. But experimental systems can make this rate 10 times faster and cram 20,000 conversations onto each fibre. A cable the size of a pencil can bring hundreds of television channels into your home. You would need this thick metal cable with all these cores to transmit the same amount of information that can be sent down this one fibre optic cable. Optical fibre is much cheaper than copper. It's made of silica, which is pure sand. Year by year, the price of copper and iron increases, while optical cable is getting cheaper. And there are many other advantages. We can send laser light pulses down a glass thread for about 30 kilometers before the signal is weakened or attenuated and needs to be amplified through a repeater station. Scientists have experimented in sending light signals as far as 100 kilometers without additional amplification. This distance is about 50 times longer than electrical signals sent over conventional metal wire. Optical fibre is easier to install. All this old-fashioned coaxial cable is needed to do the same job as this fibre optic cable. Fibres are immune to interference and crosstalk, and optical fibre is almost impossible to tap. By the end of the century, Britain, the rest of Europe and America will have digital telephone systems, digital data links between intelligent computers, and high-definition satellite and cable television. Glass and light make an unbeatable combination. Essential tools for the digital communications of tomorrow, all made possible by the practical application of the simple physics of light reflection and light refraction. Also includes radio waves. We're used to the idea of radio waves carrying speech and music, but light can do this too. This light-emitting diode, called an LED, is controlled by a sound amplifier. British Telecom, together with others in the telecommunication industry, is using the application of science to rewire Britain. Glass cables are going under the ground, on overhead poles, and underwater. Soon, an optical link will join Britain with Europe. Light is just one part of the electromagnetic spectrum, which all traveling along a strand of the world's purest glass. This glass thread, finer than a human hair, is called an optical fibre. Today, your telephone system can turn your voice into short flashes of laser light